Hello everybody and welcome to this new video of the tutorials of generating the 2D sections on the online takeoff tool. Today we have a super dense video with the calculations. So let's go. Now we've defined all our geometry, all our flap, everything is there, and now we want to make some calculations to know if our section is nice or it's not that nice. So we're gonna go to the calculation section, we're gonna turn it on, and now we'll see that we have the same table here, the same geometry here, but on the bottom part we have these new controls that have appeared. So on the left part we're gonna see the results that we're gonna request of each run, and on the right part the inputs of each run. So here you have a little wheel. If you click on the wheel, you'll see all the graphs that can be shown to you. So let's start with the simple one, alpha versus CL, CL versus CD, and we're gonna just remove these ones. But here, if you click, you see all the parameters that you can plot versus all the parameters that you can plot in the polar plot. So on that side, we see fluid conditions. So we're gonna start with run polar data, which is filling this data that we just selected with our aero calculations. So let's first of all understand these little controls. All these sliders can have a single value or can have a range of value. These all four works exactly the same. So alpha, here now I am selecting a single value of alpha 10. As I want to run a polar, I want to run a sweep of alphas. So I want to run maybe from minus 15 degrees to plus 15 degrees. So that's what I'm going to tell him. I'm going to click in this little checkbox, and I'm going to convert alpha, instead of being a single point, of being a range. Here I'm going to select minus 15 to plus 15. So I'm going to plot polars from minus 15 to plus 15 degrees. And how many points will I want them to have? So how many calculations between minus 15 and 15 I want to have? Here I'm going to say 20. That's okay. Then here, what's the Reynolds number? On this video, we consider you have a minimum of aerodynamic knowledge. So we're not going to go to each of details of what is an alpha, what is a Reynolds. Okay, we just show you here how to select it. But we have these tools here that helps you calculating these Reynolds numbers and these CL numbers. So for example, imagine we're making, I don't know, something that goes through the air, okay, at 25 degrees, and we're gonna go at 200 kilometers per hour. We're gonna have a chord of 1 meter. We're gonna have a surface of 10 square meters, and we're gonna lift 3 tons, for example. Just for example, that's a bit too much. We're gonna put a bit more surface. 15 square meters. There we go. So here, once you've selected the fluid and the conditions, you can have the CL number that you're calculating. So then we'll see on the calculations where to see the CL number, the Reynolds numbers, and the Mach. So here, for example, in this case, I will run 3.5 millions. I can just copy this value and come back here to my test section and say I'm gonna run Reynolds of 3.5. Then this other value is nquit. Nquit shouldn't affect too much the lift, but will affect a lot the drag. Nquit is an X-foil parameter that helps you to calibrate the way the transition happens on your section. So it can go, if you have a super smooth flow, for example, a wind tunnel, and you have a super smooth surface, the nquit grows because the flow can easily manage to have a very long laminar region. If you have smaller nquits, the transition is triggered earlier, so maybe because you have a rough surface, maybe because you have a very turbulent flow. So it goes normally from very small values as 0.1, 0.2 to very big values of 9. You can see the documentation of X-foil. So said that, this tool will calculate on the background. We have 2 ways of calculating it in this fast mode. One of them is X-foil, that we've recompiled the source code to be as fast as possible, and the other one is neural network over some X-foil results to make calculations way faster. by default normally use the neural network one. So this enquete, we're going to let it, for example, 1, which used to be, let's say, the main default value, and the Mach number, let's put it very small. Then here you can choose the fluid and the elevation, and this is especially for cavitation on the water. It's really dependent on the elevation or how deep you are into the water. So okay, we have all the inputs. We're running a neural network, so the fast one, and we're gonna use the flap we have on the section. So I don't know what flap we have, -4, so let's put it to 0. And we're gonna run exactly this geometry. If you run Polar Data, you will see that it runs pretty fast, and you see the two results we've selected. So alpha versus CL, and CL versus CD. As it runs so fast, you can click Auto Run, and each time you modify a parameter, it will rerun it. So for example, here, imagine we want to study a bit more the stall. We want to increase the value of the alpha, and here we already captured the stall, and the stall on the negative side. So that's a really nice curve. But now, the beauty of it is that if you modify some parameters here, so let's imagine I'm gonna modify my control points, you'll see live the impact on the result. And that's a really big help. Not only that, but you can also understand how the parameters affect your design. So for example, imagine I'm gonna duplicate this section. And now, for example, let me see how the leading edge radius affects the design. So I'm going to change the leading edge radius. Instead of 0.7, I'm going to point 1.3. I instantly see the results on my section, and I instantly see the results impact on my analysis, which is very nice. So on that case, we see that at higher CL, at higher angles of attack, we achieve to have more CL, so we delay the stall, which is an expected behavior of increasing the leading edge radius. But here, of course, we're paying some drag. So the CL versus the drag, the red has higher drag than the yellow. And the good thing is, it's not only leading edge radius, but for example, we can come back here, put 0.7, and now start playing with the thickness. What happened with my thickness of 13? What happened if I put 14? Again, I see an improvement on the stall, and I guess I'm degrading not that much the drag. If I want more definition, I just need to add a little bit more points, and it will add some more points on this zone. So now I can see the results on this zone. I can add a third section, so all the sections that are visible are going to be calculated. So here, for example, I can make another jump, and I have all the picture on how the thickness affects my section design. Okay, so now let's have a look a little bit. A part of making single lines, so single polar lines, we can also move in other parameters. So let me just leave a couple of sections to have cleaner plots. And now what we're going to play with is, for example, the flap. Here I have this little checkbox activated that says use section flap, which means that this curve corresponds to the flap the section has. So here in my section, if I put on the red one 5 degrees, I'm increasing the camber. If I put -5, I'm decreasing the camber, and you see, oh, I've put -13. That was too much. -5, you see how it changes. And the same if I select the yellow one, I put 5, and now I'm comparing the polars of the different flap angles, okay? But what I can do is, instead of putting a single flap value, I'm gonna be able here to change the flap angle. So if I deactivate that, I see the flap appearing, and it's exactly the same as before. So I have a single value now. So now both sections have flap 9, both sections have flap 5, both sections have flap -16. And again, I can make this being a range of values. So now I want to go from -2 to 2, and I want to input to have a sweep with 3 values, for example. And now I see the different curves at different flap angles that I can compare with. So instead of here, let's put it slightly more to have a bit more step. And again, you see live how the flap affects each of the sections. I'm going to reduce a little bit the alpha so I can compare a bit more the drag. And here I have all my curves with drag curves to be able to compare. I can also sweep not only with flap, but for example, I want to see the sensitivity with the Reynolds. So instead of having Reynolds 8, Reynolds 11, Reynolds 0, Reynolds, I can also make here a range. So let's go from Reynolds 1 million, all the Reynolds are in millions, to 10, for example. And let's put 3 values. So that's how the section properties evolve with the Reynolds. I can put more values and see how we transition from 1 to Reynolds 10 with 6 different graphics. And the same for the NCRIT. So I'm going to let here the 5.5 and I can study how the NCRIT affects my analysis. So if I put NCRIT 0.2, and now I want to sweep from 0.2 to, for example, 1.2.45. So the NCRIT 0.2 results are the ones with a line, and the NCRIT 2.45, the drag is lowering. So normally the higher the NCRIT, the more laminar zone we have. The transition is moved aft downstream. So the NCRIT doesn't affect that much to the CL, but affects a lot the drag. And again, I can understand the sensibility of my sections to the NCRIT. And again, the same with the Mach. Now I'm with this low Mach, but I can change the Mach and understand how this affects to my section. Again, I can put a range from Mach 0.1 to Mach 0.7, for example, which is pre-transonic mode. And you see here the drag and the lift is hugely affected. We'll see a little bit later how the different plots that we can do here. Now let's go to run section data. And to do so, we're going to hide the red curve and we're just going to focus on this yellow one. And we're just going to put a single angle. So alpha 0, flap 0, Reynolds 5.5, NCRIT, and Mach. And I want to see how the CPs evolve on my section. So here is the lower geometry, the lower skin. That's the transition point. Here's the upper geometry, that's the transition point, and that's the CP evolution. This neural network has been trained with some points over the chord, and if here we want more details, we could run an Airfoil. So here we have the comparison between the CPs, strong line from the neural network, and the CPs from Airfoil, which are these ones. So the first 2% of the chord we're missing some values, but the rest you see how well it matches, and that's the transition of the two different models, which match pretty well. And now here I can change my angle of attack and see how the pressure distribution changes on my section. And not only that, but I can also see live while modifying my geometry. So for example, here I have a little dip. I want to increase it a little bit, up, and there we go. And I see live how my geometry is evolving. So maybe I want to make more laminarity on the top part. Let's see if I achieve it. Not that easy. There you go, I'm pushing the laminarity aft. There you go, the laminarity goes up. So I can understand really quickly how by modifying my geometry, both in my control points or directly with my parameters how it does affect the results. So here I'm changing the camber, and I see directly how it affects my pressure distribution. I'm changing the thickness, and I see how it affects my pressure distribution. Again, here I can make sweep of values. So for example, imagine from -13 to 17, so that's a big sweep. Even if here we put 51, it's limited to 6. So here I have the two solvers, so maybe I'm gonna hide the Xfoil. And here I see the graph of all my points. Let's put smaller range of values, so from -5 to 5, for example, and then maybe to be able to read them 4 curves. So here I see the red ones are the top surface and how the CP is evolving and how the transition is evolving at the different angle of attack. Not only at different angle of attack, but also the same as before at different flap angles, at different Reynolds. You see here the pressure distribution with Reynolds doesn't change that much, but the transition is moving forward and aft. And for the end quit, it's going to be more or less the same. Look at the transition from end quit 0.2 to 2.45. The transition will come from here to here. And I can quickly understand how all these parameters affect each other. Good. So now let's have a look on this bottom part. Let's come back to a polar, so run polar. Only 4 points. Let's put a bit more points here to have a bit more definition. There we go, and a bit bigger. There we go. That's my polar. First of all, let's have a quick look on all the parameters that we can put. One interesting parameter, for example, is the CM, is the pitching moment of the section. So that's with the CL, how the pitching moment changes. So the more CL we have, the more tendency it will have to pitch down. And again, you can copy your section and try to understand how to change my section so that this zone here doesn't go that deep. And you will have a pitch stable section. There you go, for example. Normally, putting a bit of reflex here behind, you're able to control this pitching moment. Let's see, other important parameters. We can see CL versus top and bottom transition. CL versus top and bottom transition. So here that means at CL0, the top transition of the yellow is at 0.42 of the chord, so 42% of the chord. So again, I can modify my parameters to try to understand if I can push aft my transition and gain a little bit of drag. And the same with the bottom transition. What else can we plot here? We can plot inception speed, which is very important for cavitation. The inception speed is the speed at which the section will start cavitating. So let's put it compared to its CL. So CL versus inception speed. And here we go. So that means if we just sweep the alpha, at CL 0.13, the section will start cavitating at 37 knots. And again, I can start playing with my design to try to understand how to make it grow. Normally, the thinner the section is, the better it will be in terms of cavitation. What I really want to do is minimize the acceleration on the suction side to minimize the increase in suction. So I want something really smooth. I want to reduce as much as possible the curvature, and I will be able to push the cavitation up, as you see. What else? We have other parameters. For example, the CP min. I can see how CP min evolves with the CL. which will be more or less the same as the cavitation plots. So that's a little bit all what we have. Okay, I wanted to show you also something. Let's remove a little bit of plots here. So I wanted to show you also different plots mode. Imagine I'm sweeping two variables. I can sweep flap and angle. Here I can use something that is called envelope. So here it's hard to see all the graphs, and envelopes will just plot the envelope of all these results. So I can see here now that clearly the brown section has way better cavitation properties compared to the yellow one, and I see that the yellow one is way better in terms of drag, especially on all this zone, and this envelopes all the results. You can not only plot absolute values, but you can also compare relative values, one versus another. So you can compare the value you're sweeping, so alpha, versus each of the parameters that you had selected. So here the brown section, it has less drag up to alpha 2.25, then has more drag, and then has less. And you can have the relative or the ratio of drag. Well, to be able to run automatically each time I modify something, you click on this auto run. If you deactivate it, you have to press each time the run button. Coming back to the section data, we can compare sections CPs between each of them. So let's put a single case to be able to see something. And now I can compare the pressure distribution on one versus the other. So here you can clearly see that this one has way more suction here at the high curvature zone, and that's why it has less good cavitation properties. And this one is gutted here, so the cavitation properties are well improved. You can plot CP, but you can also plot the derivative of the CP, which is very useful to, I'm gonna put the auto run again, to see the risks of separation. Normally the higher the derivative is, so when I'm passing from negative values to positive values, at some point, if this gradient is very big, we can have risk of separation. And we know that Airfoil doesn't capture well the separation drag. I mean, it's totally off. So the safest thing to do in Airfoil is try to minimize the risk of separation. So the gradient could be a good way of checking this separation. And then also we can plot the Stratford coefficient, that the gradient, the more downstream this gradient is, where the bundle area starts to be big, the more risk of separation we have. So this Stratford coefficient basically weights the pressure gradient with the position in the chord. And from a certain value you have risk of separation. So if you have a strong pressure gradient really at the end of the chord of the section, you will have more risk of separation than at the beginning, and this ponderates that. More or less around -4, -6, you can have some risk of separation. But the idea of that is taking from a section that you know that doesn't trigger separation, you can have a reference and say, for example, I don't want to be higher than that. So for example, the brown one, I could make a bit more pressure gradient here, knowing that I don't want to cross these limits, for example, that I know it won't separate on the yellow one by experience. Maybe I've already built the yellow one and that's my reference one. So I know this Stratford coefficient doesn't have to be lower than the yellow one. Okay, and now here we have, so all these results, you can export it in a CSV format, or in this sim format is a format for the simulator that we used to use for our boats. I will make a specific video on that for the ones that are interested. It's a super nice simulator that simulates all the physics, so you can test your designs in this tool and understand which one is better while maneuvering, which one has more stability, and which one go just faster. I will let the link here below, so if you're interested. And I think we cover all the options that we have here. Again, please give us feedback. It's hard to know what's the on what fields maybe I've went too fast, or I need to put more detail. So please feel free to comment. We'll come back to any of the points that you want. Maybe someday we make a live video and we all together start to build a section. Also, if you want, maybe as an example, let's say, why don't you design a section for a foil, and we can make a quick tutorial video on designing a section for a specific foil, for a specific A class or wing foil or whatever. We'll do some kind of this, but really we're really interested on what's interesting for you to continue making these kind of videos. That's a bit all for the video of today. Thank you so much if you reach this moment. Pretty long video, pretty deep video with a lot of things. I hope it was useful for you, that you learned something, and that this will help you your work in some way. Again, thank you very much, and see you on the next video. Bye bye.